We'll start in a minute. It's almost, well, it is 11:15, but I'll wait a couple of minutes. Okay, good morning. So, are there any questions on the homework problems or anything else?
On the lab report,
Yes.
do you want us to do graph 3 still or no?
Graph 3, yeah, sure.
Okay.
You follow
On that
the,
data, you had it like X'd out.
that's not your graph 3. You follow the template.
Okay.
You downloaded template, right?
I mean, I have like an Excel thing and I can make it to where I can make my graph where it's the area under the curve.
Yeah, that's it. Yep.
Okay.
Yeah. You're doing well. Okay, so we'll finish up chapter. I'm pretty much done what I wanted to do in chapter 5. There's not a whole lot in chapter 6. I'll talk about it today. We'll finish it up, and then we'll have a test on 5 and 6 on Friday. There's only 5 homework problems. I think it's 5 in chapter 6, and I'll post those right after we get finished today. And so you'll have time to do those tomorrow or today and ask questions about them tomorrow. So we will have a test on Friday. Same format. 10:45, around 10:45. Get it back to me by 12:45, okay? Okay. So are there any questions we talked, on the stuff we talked about yesterday, friction and so forth? All right. So I want to talk about this idea of uniform circular motion, We talked a little bit about that when we did projectile motion and accelerations and so forth. So it's the same sort of setup. You have an object that's rotating in a circle, but now we're going to give it a mass m. And the previous stuff we did, we just said it's an object rotating. We didn't know anything about the mass of the object. So give it some mass m. It's rotating at some radius r, and it has a tangential velocity v. We already know that the acceleration of the object is in this direction towards the center. That's AC. That's the centripetal acceleration. By the first law, the object would naturally want to go straight. For it to be going in a circle, it requires some force. It requires an external agent to move that object in a circle. Okay? So that force is in the same direction as the centripetal acceleration. So it is, I'll try to draw it here. That's F, I'll call it F sub C. That's F centripetal. So that's a center-seeking force. Just like you would expect, we already know that the centripetal acceleration is v squared over r. So mass times acceleration is force. So the centripetal force, F centripetal, is equal to m. Let me write it like this, MAC, which is equal to the mass times v squared over r. So that would be the force required to move that object in a circle based on its radius and its velocity or magnitude of its tangential velocity. Whether it be a string or the wind blowing, making it move in a circle, a water currents making this object move in a circle, whatever it is, it requires this amount of force, the mass times the velocity squared divided by the radius, all right? And objects moving in circles do require quite a lot of force to keep them going in a circle. I'm going to do a calculation in a second. I think I left my stupid calculator in the house again. Anyway, so rotating objects, especially even if they're small objects and they're rotating very, very quickly, it is a lot of force. It's a large amount of force to keep those objects moving in a circle. And if you've ever seen a rotating object like an industrial object or something like that that's rotating very fast and it starts to break apart, I mean, it throws things everywhere at really high speed. So we'll do a calculation here in a second. This centripetal force, I already mentioned it's toward the center. You may have heard of this term centrifugal or centrifugal forces. Those are so-called fictitious forces that it feels like if you're in that frame of reference, like you're going, I always use automobile examples, but if you're riding in your car and you're turning a corner very quickly, it feels like you're being pressed against the side of the seat. That would be, in your environment, a centrifugal or centrifugal force. That's a fictitious force. The actual force is the car pushing you in a circle. So you're feeling that reaction force. The action force is the car pushing you in a circle, and you're feeling that reactive force that you have, okay? So we're not going to talk about centrifugal forces very much. Centripetal forces are the ones that make these objects move in a circle. So let's take a typical example. Let's say that you have a radius of about 10 centimeters. So, 10 centimeters is about like this. So it's a diameter, maybe about like that. It's a wheel, okay? And it's rotating at, let me give it a rotational speed. Let's say just something reasonable, about 100 revs per second. That's pretty slow as things go. Okay, 100 revs per second. That's 6,000 revs per minute. That's fairly slow. Okay, so this would be the frequency. That's 1 over the period. And let's put a little, say, 20-gram object. 20 grams, a little small mass. Okay, if you've been in the lab, I know some of you may have. The little 10-gram masses, they're about that big, and okay, little small mass. So let's see what kind of force you would need to keep this 10-gram mass, 20-gram mass moving in a circle at this frequency. Okay. So I'm going to convert this to period. It really doesn't matter. Remember, V is equal to 2 pi R over T. T is equal to 1 over F. That's the so-called natural frequency, not the angular frequency. When we start talking about rotations, we'll look at angular frequencies. And the only difference is the angular frequencies will include the 2 pi. Okay? So V is equal to 2 pi RF, and this is the frequency, 100 per second. That's one time around, all right, or it's 100 times around every second. This has another name, hertz. Okay, so let's calculate V. So V is equal to 2 pi times R. R is 10 centimeters, so that's 0.10 meters. That has to be in meters. And F is equal to, so I made this calculation pretty easy, 100 per second. Okay, so this is equal to 20 pi. Okay, so V is equal to 20 pi. I'll plug that in. I'm not doing very good with my board work today, but okay. Plug it, yeah, okay. So FC equal to mv squared over R. So this is equal to 20 grams, so that's 0.020 kilograms times V squared, well, that's 400 pi squared divided by R, which is 0.10 meters. Okay. So we do this calculation, what do we get? Let's see. This becomes 4,000 pi squared. So you get 0.020 kilograms times 4,000 pi squared meters per second squared, and that is equal to what? 8, and then I'll take off 2, so that's 80 pi squared, maybe? Can somebody help me with that?
You're right.
80 pi squared kilogram meter per second squared. Okay, so that's newtons. So 80 times 9, That's about 720 newtons. What do you get numerically here? 730 or?
I got 789.57.
Okay. 789 point what?
57.
6. Okay. So almost 800 newtons to keep this little 20-gram mass moving in a circle that's only a radius of 10 centimeters. Okay. So that's a lot of force. Remember, about 100 newtons is about a kilogram of mass in the gravitational field. So this is about 7 or 8 kilograms. Okay, it's a lot. All right. Are there any questions on this calculation? Very simple. You just an object going in a circle. You know the mass, you know the radius, and so forth. Okay, so I want to look at a little more complicated situation. Thinking about an object now including the gravitational force, okay? Like an object, I wish I had something on a string. What have I got? I don't have any string in here. Yeah. Oh well. Oh, here's something. Okay. Here's a charger. All right. Forget about this part at the top. Okay, so this thing's dangling from this little wire, and I'm moving it in a circle like this, okay? So what forces are acting on the object when it's going round and round like this? Well, I'm going to try to draw a free body diagram of that. Let's say that I take a snapshot of it just as it's moving around, and here's that point where it was, where my finger was, and here's the object going in a circle, okay? So it's moving around like that. So I took a little snapshot, and that's what it looked like, okay? So something's holding it up here. This is an object of mass m, okay? What forces are acting on this object? Let's draw a free body diagram. Well, there's definitely some tension in the string, okay? Tension in the string, and there's also gravity. Anything else acting on the object? Nope. That's it. Okay? The tension force is not only making it go in a circle, it's keeping it elevated like this. All right? The object wants to go straight or in a straight line, and this tension force is keeping it going in a circle. But what happens is, also due to this tension, you get this interplay between the gravitational force and tension. So you're not only making the object go in a circle, you're lifting it with the tension force. So if this angle is theta, now I can define this angle, this angle here as theta. It really doesn't matter. But if this angle is theta, then breaking that into components, I have I have t cosine theta, mg, and t sine theta in this direction. Remember, it's moving in a circle. There's a velocity in my snapshot. Let's say if I'm looking from the top, it's going clockwise. So there's a velocity. That little circle, oops, that would be out of the board. The little circle with the x means there's a vector going into the board, okay? So the velocity is in that direction. So this would be the centripetal force. T sine theta is that centripetal force. T cosine theta is this lifting, what I'm going to call a lifting force that's raising the object, okay? And you get to the point where you're in equilibrium like I was doing, where I had it going at a nice, constant sort of angle, okay? When these two forces are equal to one another, there's no more acceleration. The object stops, okay? And this is static in this direction. There's no acceleration in this direction. However, there is an acceleration in this direction, right? There's a constant acceleration in that centripetal direction. So, t cosine theta will make up positive. So this will be, I'll call it the y direction. T cosine theta minus mg is equal to 0. No acceleration. It's in equilibrium in that direction. It's static. So t cosine theta, and this is usually the key to solving these type problems. You'll be given an angle, okay? Possibly you'll be given an angle and the mass, and by knowing the angle and the mass, you can solve for the tension. Just like doing a two-dimensional projectile problem, okay? You're going to look at something in that y direction, maybe solve something in that direction, and then use that information to solve for the centripetal direction. So in the r direction, I'll call that the radial direction, okay? If I'm looking down on this object going in a circle, all right, that radius of that circle that it makes, I'm calling that the radial direction. So in the r direction, the force is equal to t sine theta, and that equals mv squared over r. The force, this is simply force equals mass times acceleration, where that r is the projection of that circle that it's making if you're looking from the top or the bottom, okay? All right. I think there's one homework problem maybe in chapter 6 based on this. All right. Are there any questions on this idea? I know I did a real sort of technical explanation, but hopefully you understand this. What I'd like to do is just let you look at these homework problems, and if you have questions, we can deal with those tomorrow. Okay. And like I said, let me draw one more picture just to give you an idea of what I'm talking about as far as R. In the picture I had, let's say here's, the object, it's rotating, mass m. So thinking of a vertical here, this was theta, then this is the distance r. Okay? If I'm looking from the top down, that would be the circle that the object is tracing out. Oftentimes you may be given this length L. You can find a relationship between R and L and theta. That's pretty simple. Okay. All right, so that's about it for circular motion and forces. I do want to spend a minute talking about terminal velocity. So this is something that combines the stuff we did with free fall and forces. Oh no. Sorry about that. A friend of mine calling. He can wait. Okay, terminal velocity. Anybody familiar with parachuting and jumping out of planes and all that stuff?
Is terminal velocity like whenever you fall and then you can't fall any faster because of the weight or something like that?
Yeah, you're on the right track, okay? When you start to, let's say you are in an airplane, you're about to parachute, you jump out of the plane and you're spread out like this. So you're falling flat and you're spread out. You come to a point where you start falling at a constant velocity or speed, okay? You're falling at a constant speed. You're not accelerating. That point is reached where the force due to gravity is equal to this resistive force or so-called drag force from the air resistance. And the air resistance, a pretty decent model for air resistance in objects moving, that resistive force goes like v squared. So it's some function of the velocity squared. And we could talk about the reasons. If you do advanced mechanics and things like that, you can talk about the reasons why it goes like v squared. There may be a linear term there. We usually ignore that. There may be a cubic term that has some effect on this resistive force or drag force. But yeah, that's the idea. So it depends on several factors. It depends on the density of the fluid, be it air, water, oil, syrup, okay? There was an old commercial back in the 1960s for Prell shampoo. Prell was a big name in shampoo. You had Head and Shoulders, Prell, I can't remember. There weren't many, okay? There were 2 or 3 things you could wash your hair with. Nevertheless, with Prell, they had a commercial where they would take like a cheap shampoo and they would drop a pearl in it and it would just fall. Then you take Prell and you drop the pearl in Prell and it falls kind of fast and then it just goes at a constant, very slow, constant velocity. So that's the idea of terminal velocity. Prell was thicker, it reached terminal velocity a lot faster, and the terminal velocity was a lot less than the cheap stuff, okay? So it depends on the density of the fluid, may depend on the viscosity of the fluid. It certainly depends on the area of the object that's falling. Why do you open a parachute when you go parachuting? Because you get a big area and you decrease your terminal velocity, okay? So you slow down even more when you open that big parachute. It also depends on the shape of the object. You know this from fast cars and so forth, opposed to, the old mom and pop sedans and everything. A really fast supercar is very aerodynamic. It's like a knife blade. They want to lower that drag coefficient or they want to low. I mean, it's in the end you want to lower that resistive force from air resistance, okay? And you do that by changing the shape. And people spend their whole careers working on these type problems. And some of them make lots and lots of money figuring out better and better ways to decrease this resistive force, okay? Or manage it. Okay, that's my speech. So I don't know, I do this every time, but I don't know if our book uses a D or an R. Doesn't really matter. Okay. I'm going to use an R, I think. Yeah. Okay, so imagine an object falling. This is mg. It's falling under the influence of gravity. If there were no air resistance, because, we've been ignoring air resistance the whole time. If there's no air resistance, you know that it falls at an acceleration g. It's independent of the mass. Let's talk about that for a second, okay? Newton's second law said, let's ignore air resistance. Newton's second law says that F equals ma. So the force on this object, an object falling under the influence of gravity with this acceleration g, the force is mg. That equals ma. The acceleration equals g. It's independent of the mass. All right, Galileo knew this long before Newton. Okay, he knew this with inclined planes and the famous legend of him getting up on the Leaning Tower of Pisa and dropping a big heavy object and a small object, and they fall and they hit the ground at the same time. Okay, and they pretty much will if they're very heavy and it's a short fall distance. Okay. The air resistance is there, but it's fairly negligible. Okay, so if there's no air resistance, then all objects fall with an acceleration of g. But once you introduce air, it's a different story, a really, really different story. Because now you have this resistive force, which I'm going to call R. Okay? So that resistive force, just like I was talking about, is based on several factors. And once R magnitude equals mg, it's no longer accelerating, right? Those two forces are equal. The net force, this is terminal velocity. The net force on the object is equal to 0, and it falls at a constant speed or a constant velocity. Okay? So R here's our model. R is going to be equal to 1/2 d rho a v squared. Okay? So let me tell you what these things are. This is the drag coefficient. Okay? That's what I'm talking about as far as the shape of the object. Is the object round? Is it square? Is it, a weird shape, okay, that you may have to do some experimental work with to figure out this drag coefficient. I don't know. But it's just based on the shape of the object. This is rho. This is the density of the fluid. Air is a fluid in the sense of, it moves around and things like that. It flows, okay? This is density. This is the area of the object. This would be like the cross-sectional area, okay? So that cross-section of the object that's falling, like the parachute, if I'm looking at it, velocity vectors in this way, and I'm looking from the top, I'm looking at that area of the top of the parachute, okay? This is velocity. I don't have to tell you what that is, all right? And this is when terminal velocity happens, when this resistive force equals mg. So we're going to set those two equal to one another. And mg is equal to 1/2 d rho a v. I'm going to put a little t there. That means terminal velocity. So we'll solve for the terminal velocity. So you get vt is equal to 2 mg divided by d rho a, and all of that underneath the radical. And I hope I got that right. Yeah. Okay. So to calculate the terminal velocity, that is this equation. Okay. Drag coefficient, density, cross-sectional area, mass, G2. 2 is just 2, poor old 2. Doesn't even get any units. Okay. By the way, this drag coefficient is unitless as well. So let's calculate the terminal velocity. Uh-oh, I think I got a visitor. What do you need? What do you need?
Nothing, I'll get there.
Okay. Sorry about that. Okay, so let's calculate the terminal velocity for an object like a person moving in air. So if you look up, I know you all are at your computers. If you go on Wikipedia, let me get on this laptop here. And type in, or just Google drag coefficient. And the first thing that I got was drag coefficient Wikipedia. And they've got then they got something wanting money. Okay, so if you look on the right-hand side there, I'll just show it to you on, let me get on here. Let's see, I need Google. Hold on a second. Okay. Come on. Okay. Okay. Hold on. Share web browser. Oh, I don't want to do that. Hold on. Okay. Okay, there we go. Can you see that? Somebody say yes or no. Is anybody listening?
Yes, we can see that.
Okay. So there's a sphere. Drag coefficient is 0.47, a half sphere, cone, a cube, cylinder. There's a streamlined body. Look how much difference it makes if you have something streamlined like an air wing. 0.04. So that's the so-called boat tail. Okay. So let's assume a spherical human. Or, well, we'll just assume a sphere about the mass of a human being. Okay. All right. So let's say we have a sphere that is falling and it has a diameter of 1 meter. I'm going to make this calculation simple. Mass, that's a meter. Mass, let's make it pretty heavy. So it's a meter diameter sphere. Well, you know, a person, if you take me and measure my cross-sectional area, I don't know, maybe it'll be about a square meter, something like that. Let's say it has, well, this is going to be bigger than a square meter for the cross-sectional area, but let's say the mass is about 80 kilograms. Okay, that's about 176, something like that, pound person. Rho. Anybody happen to know the density of air? How heavy is air? We need this in a cubic meter. I actually calculated this from first principles, from the things I had barely remembered from chemistry. I did that one time in a class, and I looked around, everybody was asleep, but anyway.
1.2 kilograms.
Yeah, it's about 1.2 kilograms per cubic meter. So if you pick up a cubic meter, a cube that's a meter by a meter by a meter, it weighs about 1.2 kilograms. Okay. So 1.2 kilograms per cubic meter. All right. What else do we need? We need D. Big D, that's the drag coefficient. So I'm going to use what we saw for the sphere. I'm going to make it a little simpler. I'm going to make it 0.5, and that's unitless. Yeah. Okay. I think that's all we need. So let us calculate the terminal velocity for this 80 kilogram sphere. Get rid of that. Okay, well, we need the area, so this is a 1 meter diameter, so A is equal to pi times 0.5 meters squared, right? So this is equal to 0.25 pi square meters. Okay. All right. So I'm going to plug it into here. So V terminal is equal to 2 times 80 kilograms times 9.8 meters per second squared divided by D, 0.5, times rho, 1.2. Kilograms per cubic meter. And the area is 0.25 pi pi. So I can erase this. What's the units here? Oh, meters. What did I have down there? The square meters. Okay. To the unit, and all of this to the 1/2. Okay. Oh boy. What do you get? Can somebody please calculate this, and we'll, I guess, Brooke, are you out there? Aren't you the calculator wizard? Well, that goes away. That becomes a 4. That's
I got 57.68.
57 point what?
68.
Okay. Meters per second. Pretty fast. What did we calculate the other day? 40 kilometers per hour is about 16 meters per second or something. All right. So you can do all kinds of fun calculations with this based on parachute opening, or based on doing a nosedive versus being spread out, how much your velocity, terminal velocity changes, different fluids. You dive into a pool, what's your terminal velocity? All right, all kinds of fun stuff. So are there any questions on this? Okay. I do want to look at one of those problems that's in chapter 5. Maybe a couple of them. Let's see. Those look okay. Number 6 is a little bit tricky, but I'll let you try it if you have questions. Number 8's a good one. Number 10's a good one. I want to talk about number 11. Nick. Okay. So number 11, if you could open up WebAssign and look at chapter 5, number 11. An inventive child named Nick wants to reach an apple in a tree without climbing the tree. Sitting in a chair, go ahead. Sitting in a chair connected to a rope that passes over a frictionless pulley, Nick pulls on the loose end of the rope with such a force that the spring scale reads 350 newtons. Nick's true weight is 240 newtons, and the chair weighs 160 newtons. Nick's feet are not touching the ground. Okay. So it has you calculate the acceleration, the force, and so forth. So this is a classic problem called a bosun's chair. So I just want to look at, just to give you a start on this problem, look at the forces acting on, here's the little chair, okay? There's a rope going over a pulley, and then there's a person, how do I draw this? I can't draw anything, by the way. Here's the little chair. There's a person sitting in the chair, and they're pulling up on the rope. Okay? That is terrible. It's like the worst drawing I've ever seen. Oh my God. It's horrible. That's even worse. Okay. Look at the picture in the book. All right. So they're pulling on this rope. It's not curvy like that. The rope is taut and the pulley is hanging from the top of the board. Okay. Well, they're actually, the pulley's in a tree. Is this even possible? I guess by now, since I said bosun's chair, a bosun is a ship's mate. A bosun in the Navy or naval terms, that's a guy who, raises the sails and ties ropes, and he's a ship's mate, okay? So, yeah, it's possible. So when you're pulling on that rope, not only are you pulling yourself up, that rope is attached and it's pulling the chair up. Okay? So if you look at a free body diagram of the chair, all right, plus Nick, plus the person, there are two upward forces and one downward force. And these two upward forces are the tensions, or the tension in the rope. Because you're pulling it, that's one upward force, and it's also pulling on the chair. So this actually ends up being a way that you can lift yourself up easier than just pulling up with one rope. Okay? This obviously is mg. This is the mass of the whole thing. All right? That's the idea of the bosun's chair. So when you do the calculation in the y direction, it's 2t minus mg is equal to ma. Okay? And you know the tension in the rope. They give you that. They said that there's a little spring scale connected to the rope, and it's reading 350 newtons, something like that. Okay? Think of it like this. People, everybody, it's a little counterintuitive. You might not catch it right away. But just think about being there stationary, okay? If you're not accelerating, if you're just sitting there holding yourself, this is definitely true. But it's also true when you start to accelerate, okay? If you're hanging from what you're doing, you're in the gym and you want to do some pull-ups, okay? When you're hanging from one arm, this arm is supporting mg, your total mass. If you're hanging from two arms, you have mg over 2 and mg over 2. Everybody knows that it's easier to use, okay? You're getting half the needed, you only need half the force in each arm to do a pull-up, but a one-handed pull-up, you've got your entire weight. This is the same kind of game. You're holding that rope and you're pulling on it and you're pulling the chair and you up. Okay? All right. A person on the ground, let's say that there was, now Nick is no longer holding the rope, okay? He's got a friend on the ground that's helping him. And the friend is holding the rope. Okay, so the friend is raising the person up in the chair. What's the force on the chair now? In this situation, okay, In this situation, you have, let me solve this for T. T is equal to mg plus ma over 2. Just like I said, if there's no acceleration, the tension is just mg over 2. You have two supports holding you up. Now, if this person on the ground is lifting you like this, you no longer have those two supports. It's just T. It's the exact same setup, except now it's T minus mg is equal to ma, and you get T is equal to mg plus ma. Takes twice the lifting force. Takes the whole thing, mg plus however much you want to accelerate that person times m. And you all know this from hopefully some life experience of lifting something. The faster, if you want to accelerate it quicker, you got to add a lot more force. Okay? So the rope in this case, has a tension that's twice what it does in the previous case. And if I had my little pulley set up, I could show you how multiple pulleys, you can use multiple pulleys to support loads with more and more ropes or little strings, and it's much easier to lift a heavy load. We still do this now, today. This is how things are lifted. You have multiple pulleys, multiple ropes or steel cables and so forth on cranes, and you divide that load out among several different or many different steel cables. Okay. All right, and you can get into all kinds of fun stuff with this bosun's chair, different scenarios with different pulleys. You can also look at, how much. That's a good one too. Let me look at that for just 1 second. In case 1, I'm going to leave these up here. In case 1, the tension so here's the supporting pulley. This is the first case. Let's say it's hanging by a string. You had T and T, okay? And T was equal to mg plus ma over 2. So this support here will have to hold mg plus ma, right? I'm going through this fairly quickly, but I just want to make a point about this. In this first case where the person's pulling themselves up, the support is mg plus ma because it's 2 times this tension. Let's look at case 2. Case 2 is the exact same scenario, but one person's on the ground and one person is in the chair. So you have twice, this force is going to be twice this tension. So you get 2 times mg plus ma. For all you guys and gals that want to be civil engineers and so forth, you need twice the support if you're going to have a system where someone is pulling from the ground, because you're supporting that person pulling and the person in the chair. Isn't nature fascinating?